All right, welcome back, everybody. Sorry, forgot to start the video there. But again, quizzes, I'll probably get them back to you sometime within the next day or two. Just try to get a little bit more of them done and caught up. So hopefully we can get those back to you. Just so you know where we're headed. And I do have to give back. I still have the 8-1-8-2 quizzes up here, and surprisingly enough, I still have people needing to make up their 8-1-8-2 quiz. If that's you, please come talk to me. We need it. Just to kind of tell you where we're headed, we have 2 more sections to do out of Chapter 8. We've done 8-1-8-2, we took a quiz, then we did 8-3-8-4, we took a quiz, and now we're going to do 8-5 and 8-6, and then we'll do our Chapter 8 test when we're all done with that. Now, you can expect that to be coming up next Friday. Yeah, as of right now, we have that planned for next Friday, Chapter 8 test next Friday. I will tell you this. We are not really learning anything new between now and that time next Friday. We're just going to keep practicing and practicing and practicing and practicing and practicing and practicing. Because what have I said all along? The more you practice this stuff, the more repetition you have with this stuff, the better you will be at them. Now, we're going to throw a couple curveballs at you. We're going to try to see where some unique cases are. That's what we're going to do in Section 8.5. And then Section 8.6 is kind of like putting it all together. You know, think back to, factoring by grouping, factoring by GCF. Now we've got these factoring the 3-term polynomials. Sections 8.5 and 8.6 kind of say, okay, what if I just give you a polynomial? What do you do with it? How do you factor it? How do you know which method to use when? And that is when you guys struggle. That's when you guys say, well, unless you tell me what to do, I don't know what to do. Well, how do I know what to do in terms of the different types of problems? So Section 8.5 is titled Factoring Special Products. I don't know if you remember, but back in Chapter 7, we multiplied special products, ones that were like, we could still use the same rules on, but they had some fancy tricks that you could use. Same thing here with factoring those special products. We can have some special tricks to try to factor those down. Now, could we still factor them the exact same way that you did everything on your quiz yesterday? Yes. Yeah. You can still factor exactly like how we did yesterday. But I got to tell you what, the tricks make it nice and easy. Let me show you what I mean. All right. Now, I am going to say this phrase a lot over the next several days. I'm going to say this phrase a lot. The first thing that you should always do when I tell you to factor is check for a GCF. The very first thing that you should do when I tell you to factor is check for a GCF. Because I tell you what, if you can pull a GCF out of a polynomial, it's probably going to make your life a heck of a lot easier. Okay? So the first rule is always see if you can factor out a GCF. If you can factor out a GCF, do something. Then try to use our factoring rules and apply what we know. Okay? So now the directions here say, determine whether each trinomial is a perfect square. If so, factor. If not, explain. You do not have to do that. It's going to ask you to do that within the homework tonight. You do not have to do that. My directions, we're just going to change it to just factor, if possible. And that last part of those directions, if possible, implies that are all of these going to be factorable? No. Now, I will say this. Pretty much every single one of them on the homework assignments and on the quizzes have been factorable. Now, we're going to start to say, okay, it may not be factorable. And that's going to kind of frustrate some of you as well. You're going to do all this work and then maybe say in the end, oh, shoot, it's not factorable. I've got to write prime, or I've got to write not factorable. You'll notice here on the homework, I actually tell you how many within the assignment, and I'll do this pretty much the rest of our homework assignments here on out. I tell you how many are not factorable. Yeah, I'm going to tell you how many of them are not factorable because I'm not going to allow you just to say, oh, not factorable, not factorable, not factorable, prime, 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 and be like, oh, I did my homework. Look, I wrote it all prime. No, you can't do that. I am going to say to you, okay, only 4 out of all of these problems are not factorable. You can only use prime 4 times throughout the entire homework assignment. Yeah. No, that's not what I mean. I mean, 4 of them you're going to try to factor, but you're not going to be able to. It's not going to work, right? You find the factors of your last number, and there's no factors that add to get to the middle number. So let's first start off by, yes. Yeah. Do I need to raise your pass? No. Not for this one, okay. I've got x squared plus 4x plus 4. Now, is this an easy type or hard type factoring? And somebody tell me how you know whether it's an easy type or hard type. John?
Easy.
How do you know?
There's no number in front of the S.
Good. Now, I've had, it's funny, I had a lot of people on that quiz yesterday do something like this as a hard type factoring problem. I had a lot of people do it. A lot of people try to do something like this as a hard type factor. Now, will the hard type factoring method work for this? Sure. But are you going to do a lot more work than you need to? Oh, yeah. But this is an easy type because I know that there's no number out front. So this is just an x squared. So that means that all I need to do is just find the factors of 4 that add together to get 4. Well, what are they? Quite simply 2 and 2, right? 2 times 2. Now, this is a special case, the ones where you have the same number, and I'll show you why here. Now, because this is an easy type, I can go straight to my answer. I don't need to rewrite. I don't need to do anything fancy. It's just x plus 2, x plus 2. I could have done that on the quiz yesterday, right? That's easy. That was like a very easy example of one of those things. I could also write it as, if I wanted to, x plus 2 squared. And this is where the special product comes in. Remember back in chapter 7, I said, there is a funky rule for this. I could say square the first, double the product, square the last. Oh, the first number is a perfect square. The last number is a perfect square. If the first and last are a perfect square, I should check to see if those perfect squares actually end up being a perfect square in the end. Like, look, if I square root 4, I get 2 and 2, right? Same type of thing there. Let me check the next one then. Is this a perfect square? Is 9 a perfect square? Yeah, 3 times 3, right? Is 64 a perfect square? Yeah. So maybe this is one of those cases where I've got a perfect square on both parts. All right, well, is this an easy type or a hard type? I guess the first thing that I should have checked is, does this have a GCF? Are all 3 of those numbers divisible by something? Are they? What is 9 divisible by? 3. Is 15 divisible by 3? Is 64 divisible by 3? No. Do you know the divisibility check by 3? You add the digits together, and if that's divisible by 3, then the whole number is divisible by 3. Like 6 and 4, add that together, you get, is 10 divisible by 3? Then 64 is not divisible by 3. Like, let me take a really big number, 1,467. Okay, let me add those digits together. 1 plus 4 is 5, plus 6 is 11, plus 7 is 18 divisible by 3? Then this number is also divisible by 3. 1,467 divided by 3. I don't know what it is. I'd have to go to my calculator. Oh, yeah, it is divisible by 3. No. That's the divisibility check by 3. So I know that 64 is not divisible by 3. So is there a GCF? No. There's no GCF. Okay, so that means I'll have to take my first number times my last number. 9 times 64. That's going to give me a giant number, 576. I want to find the factors of 576 that add together to get negative 15. Okay, well, if both of them are perfect squares, maybe I should check to see if this number is also a perfect square. Maybe that's going to work. Ooh, it is a perfect square. But does 24 times 24 add together to get negative 15? No. It does not. Now, we can't go right away and say that this is prime just quite yet. I've got to make a list now. Okay, 576 times 1, that's going to be 578. All right, so 576 divided by 2. Well, that's not going to work. That's going to give me 300. That's no good. 576 divided by 3. That's not going to work. That's going to be 195. 576 divided by 4. No, 576 divided by 5. That doesn't work. 576 divided by 6, maybe? No, that still gives me 102. Wow, I'm really big and I'm not getting any smaller, am I? Divided by 7? Nope, that doesn't work. Divided by 8? No, that's not good. That gets me a 80. 576 divided by 9? Nope, still too big. 576 divided by 10? No. 11? No. 576 divided by 12? No, I'm getting smaller. 576 divided by 13? 576 divided by 14? No. 576 divided by 15? No, it doesn't end at a 0, so that's not going to work. Maybe divided by 16? Oh, no, because that still adds together to get 52, so that's no good. 576 divided by 17? Nope, oops, that's not going to work. 576 divided by 18? No, that's still not going to work. 576 divided by 19? Because I'm looking for 15 here. Well, even if I keep going here, even if I keep taking 576 divided by these things, as soon as I get to 24, I can stop. And I found no factors that work. You have to go through that whole process to be able to say that this is not factorable, or prime, whatever you want to say. Okay? I didn't find any values that added together to get negative 15, so we say not factorable.
I'll do that 4 times today.
What's that?
I have to do that.
Now, I'm not necessarily saying you need to write out the entire list, but I would have your calculator at your side doing that really quick in your calculator to see, are there any factors that add together to get your middle number? If there's not, then you can say that it's not factorable. Let's take a look at this one. Now, my first rule is always check for a GCF. My smallest number up there is 25. What is 25 divisible by? 5, right? Anything else? No. Okay, 90 is divisible by 5, but is 81? No, so then I can't, there's no GCF here. Well, that must mean that I need to take 81 times 25, first number times last number. Whoa, 2025. But here's a special case. Is 81 a perfect square? Okay, is 25 a perfect square? Okay, so maybe 2025 is also a perfect square. 45. It's 45 times 45, and look at that. What's my middle number? Bingo. 45 plus 45 is 90.
How would you, like, how would you, is that all we have to do? Or do we have to,
Well, now we go through the process of factoring it. 81x squared plus 45x plus 45x plus 25. So we still have to do it. It's just finding the correct factors that work. If they're both perfect squares, this might be one of those special cases where if they're both perfect squares, you can square root it and see if those factors work. All right, so we've got a 9x as my GCF to leave us with a 9x plus 5. And then we have a GCF of a 5 to leave us again with a 9x plus 5. And now this again is one of those ones where It's the same thing repeated over twice. So you can write that as your answer, or if you'd like to write it as 1, since it's the same thing, 9x plus 5 squared. That works too. So again, those are what are called perfect square trinomials. There are 3 terms that have a perfect square at the front, a perfect square at the end, and when you factor it, it comes out to be the exact same thing twice over. So those were 3 terms. You know, back in chapter 7, we learned how to multiply something that looked like this. This was a very special case, and when we FOIL that, we would get a squared plus ab minus ab minus b squared. Now, what happened with my middle term then? Oh, well, it canceled out. So that must mean that would have ended up being a squared minus b squared. And that, since chapter 8 is working from backward here, that is another special case. When you have 2 terms, and they are both perfect squares, and there's a subtraction sign in the middle of it, you can call that what's called a difference of squares. A polynomial is a difference of squares if it meets these 2 criteria. Both sets of numbers are perfect squares, and they are subtracted from one another. Okay? It's got to be what's called a difference of squares. A difference of squares. Difference implying that they're subtracting, and squares implying that they are both perfect squares. So what do you do based off of that? Well, if they are both perfect squares, you can use this rule. It's going to turn into a plus b, a minus b. You square root the first, you square root the last, and you put them in your 2 parentheses, one with a plus, one with a minus. Okay? You square root the first, you square root the last, one with a plus, one with a minus. For example here, if I have x squared minus 9, now how do you tell if a variable is a perfect square? It's got an even power. If a variable has an even power, then it's a perfect square, like x squared, x to the second, x to the fourth, x to the sixth, x to the eighth, x to the 10th. Those are all perfect squares because I can divide it by 2 and essentially take the square root. Now 9, now the number that you're looking at, you can't divide by 2. You've got to actually test to see if that's a perfect square. How do we do that within our calculators? Well, you do have a square root button, so if you really needed to, you could say the square root of 9 and test it out. It's got to be a whole number. Oh, look, the square root of 9 is 3. But I think that you should have those memorized at least up to 10. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. I actually require my Algebra 2 students to go all the way up to 20. Yeah, square 11, 121. 12 is 144. 13 is 169. 14 is 196. 15 is 225. You should know those in your brain. You should have those memorized. You shouldn't need to go to a calculator for that. But you should have just up to 10 memorized. Now, so let me take a look here. Is this a difference of squares? Does it meet the 2 criteria to be a difference of squares? Now, this first problem here, is the first term a perfect square? Is x squared a perfect square? Yes, because it's got an even power. Is 25 a perfect square? Yes, 5 times 5. Is y squared a perfect square? Yeah. So, does it meet the first criteria of all perfect squares? Yeah. Yes, it meets all of those criteria of being all perfect squares. The second criteria is it a difference? Is it a difference? Is it a subtraction? Yes. So it meets both of the criteria of being a difference of squares. When it does that, when it meets both of those criteria, you create your 2 parentheses. You write one with a minus and one with a plus. It doesn't matter which one's which. You could write the plus first, then the minus. Doesn't matter. And then I square root both of my terms. Now, when I square root x squared, I just get x. When I square root 25, I get 5. And And when I square root y squared, I just get y. And that's my answer. You square root all parts and put a minus sign in one and put a plus sign in the other. Don't believe me? Boil it back together to check. But that's the special case. That's the rule for when it's a two-term polynomial. When you see two terms, this is the only way we're going to know how to factor something that's two terms. This is the only way. It's called a difference of squares. Difference implies subtraction. Squares imply that they're all perfect squares. So let's check the next one. Now let me ask you this. Is 3 a perfect square? No. Is 9 a perfect square? Yes. Okay, even though one is and one's not, it's not a difference of squares. But there is something that I can do. What can I do? What should you always check first? If there is a GCF. Is there a GCF? What do these both of us imply? So let's remove the GCF. I would not say that this is not factorable because I can do something to it. I remove the GCF of 3 and I get p squared minus 3q to the 4th. Now, I now check to see if what's inside the parentheses is factorable. There's no more GCF. However, if it's two terms, I must check to see if it's a difference of squares. First off, is it a difference? Is there a subtraction sign in the middle?
Yes.
Yes. Is p squared a perfect square?
Yes.
Is q to the 4th a perfect square?
Yes.
Is 3 a perfect square?
No.
No. So therefore, this is not a difference of squares. I have to leave it like this. Therefore, that's my answer. Just that. I would not say that this is not factorable. Even though I can't go further, I still did something to it. It wouldn't technically be a not factorable, because I did something. Let's check our next one. Okay, be careful. What should you always check first? Is there a GCF?
Yeah.
What is it?
4.
4. The GCF is 4. So let's take it out. And these don't have any letters in common, no variables in common. So I'm going to take out this 4. I'm going to divide out this 4. And I'm going to get a 25x squared minus just a 1y squared. So I would not, right away I know I would not write this as not factorable. I did something to it. Now, let's check. It's only got two terms. The only thing I could possibly do to this is make it a difference of squares. First off, is it a difference? Is there a subtraction sign in between? Yes. Now let's check to see if these are all perfect squares. Is 25 a perfect square?
Yes.
Is x squared a perfect square?
Yes.
Is y squared a perfect square? So this is a difference of squares. We continue to write our 4 down, just drop it down there. And now we have our two sets of parentheses, one's with a minus, one's with a plus. And now I square root everything. Well, the square root of 25 is 5. The square root of x squared is just x. And the square root of y squared is just 1. And that's my answer. Don't believe me? Foil it back together. Okay, let's do another one. This is the next one you get that right. 88 minus 49 q to the 4. Or q to the 6. Okay, is there any GCF?
No.
No. You always should check a GCF first. But there's no GCF in this case. I've got a 49, which is only divisible by 7, and I don't even have a number out front of p to the 8. And watch out, those are not the same variable. P to the 8, q to the 6. No, there's no GCF. So it's two terms, and the only thing I could possibly do with a two-term polynomial, with a binomial, is factor it by a difference of squares. Is it a difference?
Yes.
Yes. Are these all perfect squares? Well, is p to the 8 a perfect square? Yeah, how do you know that a variable is a perfect square? Well?
Because its exponent is an even number.
Good. P to the 8, even number. Is 49 a perfect square?
Yes.
Yeah, if you didn't know that, just go to your calculator and square root it and see. Oh yeah, it comes out as a whole number, it's 7. Okay, is q to the 6th a perfect square? Yes, because it's even. So therefore, I know that this is a difference of squares. One with a minus, one with a plus. To find the perfect square of the variable, you just divide it by 2. So p to the 4th. And then I square root 49, I get 7. We just check that in our calculator. Q to the 6th becomes q to the 3rd. And there's my answer. Let's do another one. Again, practice, practice, practice. What should you always check first? What's my common factor? 4. My common factor is 4. So I remove it. I factor it out, just like I did at the beginning of this chapter. 16 divided by 4 is 4. 4 divided by 4 is 1. All right, now, I keep going inside the parentheses. I only see 2 terms. The only thing I can do with the 2 terms is difference of squares. Is it a difference? Is 4 a perfect square? Is x squared a perfect square? Is y to the 5th a perfect square? No. So this is not a difference of squares. I'll have to leave it like this. I would not write not factorable because I did something to it. I factored out the GCF, so it's not technically not factorable. I did something to it. I've got 121x squared minus 4y to the 8th. Okay, is there a GCF? I mean, the only thing that I could do, maybe 121 divided by 4. I know it's not divisible by 2 because it's not even. Let's see. No, there's no GCF, and they don't have any numbers or letters in common either. All right, so it's only 2 terms, so the only possible thing I could do here is do a difference of squares. So first off, is it a difference? Yes, there's a subtraction sign equal. Is 121 a perfect square? Yes. If I go to my calculator and I square root 121, I get 11. Is x squared a perfect square?
Yeah.
Is 4 a perfect square? Is y to the 8th a perfect square? So everything is a perfect square and there's a minus. So I know that I could go to my 2 parentheses, one's a minus, one's a plus. And now I can square root everything. Square root of 121 is 11. Square root of x squared is just x. Square root of 4 is 2. Square root of y to the 8th is y to the 4th. There's my answer. Questions about that? So that's how to factor something when it's only 2 terms. That's the only way you're going to know how to factor something when it's 2 terms. If it's not a difference of squares, it's not factorable, unless you could have pulled out a GCF, obviously. Okay, take a look down below there, last set of examples. Factor each polynomial using the rule for the perfect squares and the rule for differences of 2 squares. So basically just factor. Whoa, sorry. Basically just factor. Okay. What should you always check first? Is there a greatest common factor of these 3? What is it? 3. Let's pull it out. Let's remove that greatest common factor of 3. I see that all of these are divisible by 3, so let's remove it. Divide by 3 everywhere. X squared minus 4x plus 4. Now I keep going inside the parentheses. Is that an easy type or hard type now inside the parentheses? It's an easy type. Sweet. So we went from having a hard type, original problem, to an easy type now. Are there factors of 4 that add together to get negative 4? Wouldn't be positive 2 and 2. Negative 2 and negative 2. -2 times -2. So because this is an easy type, I can just go straight to my answers. No rewriting needed. Don't lose track of that GCF that we pulled out at the very beginning. That's a very common thing to do. You pull out that GCF and it just kind of floats into nowhere. Don't lose track of that GCF. Now, take a look at all three of these terms. What do they all have in common? What do they all have in common? Baker? Same variable. I know I can at least pull out an x. I know I can at least pull out an x. Now, is there any other numbers that I can pull out as well?
4.
A 4, right. It's tempting to just say 2, because they're all divisible by 2. But I can pull out a 4. So let's pull out the GCF of a 4x. Let's divide it out. See, back in section 8.2, this is all we did. We just factored out a GCF. Now we're doing something on top of it. So 4x squared plus 48 divided by 4 is 12. Knock down the power by 1. X plus 36 divided by 4 is 9, and we remove the x. You cannot stop. You've got to keep going. Look at inside the parentheses. That's a hard type. 4 and 9 make 36. Are there factors of 36 that add together to get 12? What are they? 6 and 6. 6 times 6. So you know what I do with this 4x? The same thing that I did with that -1. If I pulled out a GCF, just like I pull out a negative, I like to either, if it's on a quiz, I go straight to my answer blank and I write that 4x so I don't forget about it. Or I arrow it down like that. All right, let's keep going with the piece inside. 4x squared plus 6x plus 6x plus 9. And we factor by grouping. We pull out a 2x, leaving a 2x plus 3. We pull out a 3, leaving a 2x plus 3. So my solution is 2x plus 3, 2x plus 3. I'll leave it like that. If you'd like to combine the 2x plus 3s and make it a 2x plus 3 squared, that's totally fine. But again, that ending part it was like the entire back of the quiz yesterday, right? That factoring by grouping. The only new part that we're doing here is we're combining what we knew from the beginning of the chapter about factoring a GCF with what we were just doing in section 8.4. Let's take a look at our last one. Take a look at our last one. 9x squared minus 144. Y to the 4th. Okay, is there a GCF?
Yeah.
It's 3? Is 144 divisible by 3?
It's not.
It is, but 9 is divisible by 9, isn't it?
Yeah.
Is 144 divisible by 9?
Yeah.
Oh, chicken nuggets, look at that. My GCF is actually a 9. So x squared minus 12. No, 16. Excuse me, 16, not 12. 16 y to the 4th. Okay, so I keep going inside my parentheses. The only thing I could possibly do is test to see if it's a difference of squares. First off, is it a difference? Second thing, are these all perfect squares? And now I only look at the piece inside the parentheses. I know 9 is, but is x squared a perfect square? Is 16? Is y to the 4th? Yeah, so I know that this is a difference of squares. Minus and a plus, and then square root everything. Square root of x squared is just x. Square root of 16 is 4. Square root of y to the 4th is y to the 2nd. Remember, divided by 2. There's my answer. So the only new thing that we learned today was this whole 2-term thing. That's the only new thing that we learned. Beyond that, we're just combining old stuff with new stuff. GCFs with all of this stuff. Again, your homework page is 562, 14 to 19. 21 to 26, basically 14 to 26 becomes be 20. And then 30 to 34, and 4 of them are not factorable. Okay, I'm gonna pull up the homework page. If you'd like to get a jump on it, you can do so. It's really easy for me. Oh, I gotta turn off the